In today's video, we're going to look at Macaulay's method. So first, what is the Macaulay's method? Macaulay's method is a system of double integration that is used to find the deflection of a beam. So let's say you have a simply supported beam that is supported at both ends, and you add a point load in the middle. Now where the point load comes in contact with the beam, there will be a deflection, and this deflection can be denoted as y. Macaulay's method utilizes the bending equation in the form of m over ei is equal to d squared y over dx squared, where m is the bending moment, e is the Young's modulus, and I is the second moment of inertia. You will also notice that y, the deflection, is represented as a function over x. X can be the length of the beam at any given point. This is because the deflection doesn't occur at a specific point, but over x, which is the span of the beam. Therefore, you will have to double integrate in order to find the deflection y at any given point. So whenever you think of Macaulay's method, you should always remember the word double integration. Also, Macaulay's method uses singularity functions in the form of x minus a to the power of n. This specific singularity function deals with point loads, as we will be dealing with point loads in this video. To better understand this, we will work with an example. So let's begin. Okay, so let's look at the Macaulay's method by practicing with a question. So here we have a question. It can be a shaft or a beam that is simply supported by bearings R1 and R2, and you have point loads W1, W2, and W3. And also, the diameter of the beam is 0.04 meters, as well as the Young's modulus E is equal to 200 GPa. And so, in this question, we're supposed to find the deflections that are caused by the point loads W1, W2, and W3. So, to do this, we're going to use the Macaulay's method. So, let's begin. So, the first step in the Macaulay's method is to find the reaction forces, R1 and R2. These forces are unknown. So, we can use the equilibrium principle, or principle of moments, in order to determine these reaction forces. So, find R1 and R2. Okay, so to do that, we'll have to take one of these forces, either R1 or R2, as the pivot, and then we'll have to find the moments of the other forces that act around that pivot. So let's take R1 as the pivot. So now we'll start by finding the moment forces that act as when R1 is the pivot. So as you can remember, the formula for moments or torque is equal to the force times the perpendicular distance between the force and the pivot. And also it is important to set a direction for these forces. So let's say the forces acting upwards are negative and the forces acting downwards are positive. So let's start. According to the principle of moments, the forces acting downwards or clockwise should be balanced by the forces acting upwards or anticlockwise. So we can equate them by taking R1 as pivot. We'll start. So W1, that is 130 newtons, times the perpendicular distance to R1, as we're taking R1 as the pivot. So 130 times 0.15 meters. Same thing for W2 as well. 140, so plus, we're summing the moments acting downwards or anticlockwise, 140 times this distance from the pivot. So we have to add 0.15 plus 0.14. That'll be 0.29. Plus, this time we have a force that is acting upwards, that is R2. So since it's acting upwards, we have assigned upwards forces as negative direction. So we can put that as negative. R2, we don't know the force yet, times the distance, perpendicular distance between R2 and the pivot R1. So that's 0.15 plus 0.14 plus 0.08. And that is equal to 0.37. And then finally, W3, which is acting downwards, so it'll be positive, plus 150 newtons times distance between R1 and W3, that is the entire length of the beam. So that's 0.15 plus 0.14 plus 0.08 plus 0.07, and that is 0.44. and this is equal to 0 according to the principle of equilibrium moments. It has to be balanced. So now we just have one unknown variable, that is R2, and we can solve for R2. So let's simplify this equation and solve for R2. So since R2 is an unknown variable, I'll take it to that side, and then I will get at R2 on both sides. And then finally, when I simplify this, I will get 126.1 is equal to 0.37 R2. I divide both sides by 0.37, I should get, I'll take it to this side, R2 is equal to 340.81 newtons. Now that we have R2, it'll be easier to find R1. Remember the principle of equilibrium of moments, that the forces acting in the anticlockwise direction, the sum of the forces are equal to the sum of the forces acting in the clockwise direction. And also the forces acting upwards are equal to the forces acting downwards. So therefore, W1 plus W2 plus W3 is equal to R1 plus R2. Let me get rid of this. Now that we know what R2 is, we just have one unknown variable, R1, which we can find. So W1 is 130 plus W2 140 plus W3 150 is equal to R1, which is what we're looking for, plus R2, that is 340.81. So we make R1 the subject by taking this to that side, and then we can get is equal to R1. Therefore, when we simplify this, R1 is equal to 79.19 newtons. So now we have found the reaction forces R1 and R2. So we can proceed to the next step. So the next step is to use Macaulay's method, which is also the double integration. So let's visualize this beam. So we have R1 acting upwards here and R2 acting upwards there. And then we have forces W1 and W2 point loads acting in this position, and W3 acts at the end. So the first thing we have to do in Macaulay method is that we need to draw an X line at some point. So usually we can take it at right before the last force that is acting on the shaft of the beam. So we take this as X. And this X is what we're going to use as the pivot. Remember how we used R1 as the pivot in the previous question? In the same way, we're going to use this X line as the pivot. So we can now identify distances. So first one, this one is 0.15. It's given in the question. This one is 0.14. This distance is 0.08. And we take this entire distance from R1, the end of the shaft of the beam, to X as X. So this length here is unknown. The reason we're doing this is because the deflections that occur in the beam over the span of X, as I explained before, is unknown. We don't know where exactly the positions of the deflections are on the beam. So that is why we take them as X. So now we can use Macaulay's method in the form of the bending equation, as explained before. M over EI is equal to d squared y over dx squared. So we can take EI to this side, multiplying both sides by EI, and we will get d squared y over dx squared is equal to M. M is the bending moments of the forces, the point loads in this case, that are acting on the beam. So now what we have to do is find M, that are the bending moments that are acting as over X, which we have taken as the pivot, and then we can double integrate in order to find Y, which is the deflection. That is Macaulay's method. Okay, so let's move the diagram we drew, because we will need the diagram in order to find the bending moments. So the equation we got was d squared y over dx squared EI is equal to M. So we just have to find the bending moments at the pivot around X. So let's start with the first one. Also, we should keep in mind directions we have assigned for the forces acting upwards, which are negative, and the forces acting downwards, which are positive. So the first one is R1, and R1 acts upwards, so it will be negative. So we can write EI d squared y over dx squared is equal to R1, which we know that's 79.19. So 79.19 times the perpendicular distance between R1 and x, which we take as pivot, and that is x. So times x. Make sure to put the minus sign. Okay, and the next force is W1. W1 is acting downwards, so it'll be positive. W1 is 130 times the perpendicular distance between W1 and the pivot that we've taken, x. This distance here is equal to x, that is its entire length, minus this length over here, 0.15. So we can write it over here as 130 times x minus 0.15. And since this is point loads, the singularity functions for point loads is x minus a to the power of 1. So n over here is equal to 1. So we're just going to leave it like that. If it was for something else, it would be a different value for n. But in this video, we're dealing only with point loads. Okay, so the next one is W2. And W2 is also acting downward, so it'll be positive. So it'll be plus 140 times the perpendicular distance between W2 and the pivot x is the entire length of the beam, x minus this distance here. So minus 0.5 plus 0.14, that is 0.29. So we can write 140 times x minus 0.29. And the next one is R2. R2 is acting upwards, so it'll be negative. Negative R2, the value is 340.81 we calculated, times the perpendicular distance, which is this distance here. And this distance is the entire length, that is x minus this distance here. So it can be written as x minus 0.37. And we're going to ignore any forces that act to the right side of this x line. And so these are all the bending moments that act to the left side of the x line that we've taken as pivot. So like this, the equation is now complete. We can now start double integrating this side in order to find the deflection y. Okay, so I've rewritten the equation we made on the top, so now we can start to integrate this in order to find the deflection. So the first integration, ei dy by dx is equal to, so we first integrate this side, and if you remember, the formula for integration is x n is equal to x n plus 1 over n plus 1. So if we have a value like 2, you would get something like x2 plus 1 is 3 over 3. So let's begin integrating each of these terms. First one, minus 17.19x, and it's to the power of 1. So it'll be minus 79.19. 1 plus 1 is 2, divided by 2, plus 130 x minus 0.15. So remember, we're only integrating with respect to x. So this is a constant, and so we'll only be integrating the term that is inside the bracket that includes x. When you integrate terms that are inside brackets, it'll be something like this: x minus a to the power of n. And so when you integrate it, it'll be x minus a n plus 1 over n plus 1. It's the same as you would treat what's inside the bracket as a single value. So you would get 130, as it is a constant, x minus 0.15. Remember, this is to the power of 1, so it would be 1 plus 1, that's 2, divided by 2. Let me get rid of this. So we'll do the rest in the same way. 140, it's a constant, so x minus 0.29 is to the power of 1, so it would be 1 plus 1, 2, divided by 2. We'll continue the equation down here, minus 340.81 x minus 0.37 is to the power of 1. So that would be 1 plus 1, 2, divided by 2. And remember, when we integrate, we will always have a constant of integration. So I'll write this as c, which is unknown at the moment. So now that we have the first order of integration done, we can integrate it the second time. I've rewritten this on the top, and we're going to integrate this again. So ei times y, which is the deflection, is equal to minus 79.19 divided by, so now in this we're going to do it the same way. So it's going to be x to the power of 2, so 2 plus 1 is 3, divided by 3. So we can just multiply these two terms and we will get 6. So I'll rewrite it as 79.19 x to the power of 3 divided by 6. And we'll do the same for the other terms as well. So 130 x minus 0.15. We have 2 there, so it'll be 2 plus 1, that'll be 3. And we have 2 at the bottom as well. And we'll divide it by 3, so it'll be 2 times 3, 6. So if you didn't understand what I just did, here's just a quick breakdown. So we had a term that is x to the power of 2, right? And so we integrated this term, x to the power of 2 divided by 2. So we integrated this term. So we would get x 2 plus 1, that's the integration formula, over 2 plus 1. But we also have this half value, which is a constant. So when you integrate this, you would get x to the power of 3 over 3. And remember the half value that we had at the start. So that is why we got x to the power of 3 over 6. So that's why we're getting these 6's here. Plus 140 x minus 0.29. It's literally the same number, same term, so it'll be repeated. 2 plus 1, 3, divided by 3. So 2 times 3, 6. Minus 340.81 x minus 0.37. In the same way, this will be 3 and answer 3 times 2, 6. And also this c that we have here, we shouldn't forget it. So it'll be plus c, and if we have a constant, it automatically gets an x in integration. That will be because any constant that we have, let's say 5, is in the form x to the power of 0. Any number to the power of 0 is 1. So when we add 0 plus 1 divided by 0 plus 1, we would just get 5x. That's what we did here. And now since we've integrated this twice, this will have another constant of integration. So since we have two c's, we don't want to get confused. We will label this as c1 and this as c2. So now we have the completed equation that has been integrated twice, and we have isolated y on one side. So if we take this ei to the other side, we can solve for the deflection at any given point, provided we have the x value, the length. But first we have to find the two unknowns, that is c1 and c2. So this will bring us to the next step of the Macaulay's method, that is called boundary conditions. Okay, so in a beam we know that when a force acts or a point load acts in a specific location or position, there is a deflection that acts downwards. This is what we're looking for using the Macaulay's method. But while we don't know these boundary conditions, we can assume the boundary conditions that are acting for the reaction forces. We know that there won't be any deflections where the reaction forces occur, that is R1 and let's just say R2. So we know that the deflection at these points, as the forces acting upwards, would be 0. So with this knowledge, we can use to find the unknown variables C1 and C2. So we can assume first R1, at position R1, boundary condition y is equal to 0. So at x is equal to 0, as R1 is the start of x, so x at this point is equal to 0. We know the deflection at that point is equal to 0. So that will be the first boundary condition. The first condition is at x, when x is equal to 0, the deflection y is equal to 0. That is because the reaction force is acting upwards, so there will be 0 deflection at that point. So we can put y as 0, and we can also put x as 0. So minus 79.19 over 6 of 0. But before we write the rest, there is something very important that you must know about Macaulay method. As you know, Macaulay method uses singularity functions in the form of x minus a to the power of n. Since we're using point loads, the n's are 1, so we can neglect this at the moment. So these functions, x minus a, are only valid if x is greater than a. If x is less than a, then they are invalid, so they can be ignored. So if I put x as 0 in these equations, you can see that, for example, x minus 0.15, and we know that in this boundary condition x is equal to 0. So since 0 is less than 0.15, this is not valid. So then we don't have to write this term, we don't have to write this term, we won't have to write this term as well. So only this, and these terms are the only ones that we are valid for this equation, for this boundary condition. So therefore, it is important for us to remember this rule when we're dealing with equations in the Macaulay method. So utilizing this rule, we can now write this equation as minus 79.19 over 6, x is 0. So we know this singularity function is not valid because of the rule. This isn't valid. This is invalid. These three aren't valid because x in this situation is less than a, these a values. X is less than 0.15, x is less than 0.29, and less than 0.37. So it's just this term and these two terms. So it'll be plus c1, which is an unknown variable we're looking for. X is 0 plus c2. So we know that this side is 0 because 0 times whatever these values are will be 0. 0 times these values will be 0. c1 times 0 is 0 plus c2. So therefore c2 is equal to 0. So now we have the value for c2. Now we can find c1. For that we will need another boundary condition. We know that there is another reaction force at R2, which is somewhere over here. At R2, we know that the deflection y is 0. So at the position of R2 is x is equal to, we have 0.15 plus 0.14 plus 0.18. That's the position of R2 from x, from the position of 0, is equal to 0.15 plus 0.14 plus 0.08. So x is equal to 0.37. So now the next boundary condition we know is that when x is equal to 0.37, that's because that's where R2 is, the deflection is 0. So y is equal to 0. So we can do the same thing we did in the previous condition, substitute the x values as 0.37. When y is equal to 0, substitute y as 0, and we can solve for the next unknown, that is c1. So we can write it as ei times 0 as y 0 minus 79.19 over 6, and x now is equal to 0.37 plus, so now let's look at the singularity function rule. Is x minus 0.15? In this case, we're substituting x as 0.37. So is 0.37 greater than 0.15? Yes, it is. So this will be valid. Let's look at this one as well. Will x be greater than 0.29? Yes, this one will also be valid. Is x greater than 0.37? Nope, in this one it isn't valid. So just this term, this term, this term, and these two terms are valid for this equation. So we ignore this term. Alright, so let's continue with this equation. 130, x is 0.37 minus 0.15 to the power of 3 over 6 plus 140, x is again 0.37 minus 0.29 to the power of 3 over 6. I'm going to continue the equation downwards. We're not writing this, so we'll continue with plus c1, x is 0.37 plus, we know c2 is 0, so you can just put 0. Let me move this aside so it's not in the way. We can now rewrite this as, so we can take c1 to the other side over here, and we can simplify these terms. So we will get minus c1 0.37 is equal to, and then we simplify all of these terms, which will give you minus 0.42588. And now we divide both sides by 0.37, so c1 is equal to, remember the minus and minus cancel out, so it will be 1.1510, and this is to 4 dp. So now that we have found c1, we have found all the unknown variables, and we have therefore completed the bending equation that is needed to find the deflection at any point given you know the x value. So now we can find the deflections. We can return to the original question and find the deflections at W1, W2, and W3. So now we can complete this equation. We can rewrite this as, we can get rid of C2 as C2 is equal to 0. It's not necessary writing that. So we can rewrite C1 as 1.1510x. Don't forget the x. So this is the completed deflection equation, and now we can return to the original question and find the deflections at W1, W2, and W3. To do that, we just need the x values, that is the position of where these deflections occur, or the positions of the point load from R1, and we can substitute the x values in and find the deflection, that is y. So before we proceed further with this equation, we need to make sure that we have all the terms. So E is the Young's modulus and is already given in the question. I is the second moment of inertia, and that is something we have to calculate. So as you can see, this is a shaft and it has a diameter of 0.04 meters. So a shaft with a diameter of 0.04 meters, the formula for the second moment of inertia for a circular cross section, as this is a shaft so it's a circle, is equal to I is equal to pi d to the power 4 over 64, where d is the diameter. So that'll be pi times 0.04 to the power of 4 over 64. And this is equal to 1.2566 times 10 to the power of minus 7 m to the power of 4 meters to the power of 4. So let's write this I value somewhere else in the question like this. Now that we have all the terms, we can find the deflection at, let's start at W1. So at W1, the distance from R1 to W1, the position of the point load is x is equal to 0.15. So at W1, x is 0.15. So we can find y. EI y is equal to minus 79.19 over 6. X is 0.15, power of 3. But before we proceed further, we have to make sure that we always adhere or always obey the singularity function rule. That is, x has to be greater than a for when x minus a. Otherwise, the equation is not valid. So in this term, when x is equal to 0.5, is x over here 0.5 greater than this value? No, it is not. So this is not valid. Same thing here. X, when we sub in x as 0.15 here, is it greater than 0.29? It isn't, so it's not valid. The same thing goes here. It is not valid. So the only terms that we need for this equation to solve for W1 are this term and this term. So let's continue. And that simplifies to, now we just divide both sides by EI, and that will give you y is equal to 0.12795 over E is given, that is 200 gigapascals. So that's 10 to the power of 9 times the I value that we calculated, 1.2566 times 10 to the power of minus 7. That will give us a deflection of y is equal to 5.097. And that is equal to 5.097 times 10 to the power of minus 6 meters. And so now we know at W1, the deflection is when x is equal to 0.15, the deflection is this. So I'll write that in over here as well. So at W, now let's find the deflection at W2. We'll be using the same method we used for W1. So at W2, the position from this point is 0.15 plus 0.29. So x is equal to 0.29 because 0.15 plus 0.14. So now we can find the deflection in the same manner. EIY is equal to, and now we'll have to again adhere to the singularity function rule to know which equation is valid and which isn't. This one is valid. This one over here, x minus 0.15, when x is equal to 0.29, is it greater than 0.15? Is it greater than a? Yes, it is. So this is valid. In this case, when x is 0.1929, is it greater than 0.29? It isn't, so this isn't valid. Same thing goes here, x is less than 0.37, so this is invalid. So the only equations that are terms that are valid are this one, and this one. So let's write them. And this will simplify to 0.07135. And now we divide EI by both sides, and we know the values for E and I. That'll give us, just like we did in W1, y is equal to 2.839 times 10 to the power minus 6 meters. So let's write that down. Finally, we have to find the deflection for W3. At W3, x is equal to the full length of the beam. That is 0.15 plus 0.4 plus 0.08 plus 0.07, and that is equal to x is equal to 0.44. So we do it the same way we did earlier. Now let's see if they obey the singularity function rules. So 0.44 when x is equal to 0.44, yes, it is greater than 0.15, it is greater than 0.29, and it is greater than 0.37. That is because when x is equal to 0.44, it spans the full length of the beam. So naturally, x will be greater than a. So it includes all the terms in this equation. I've actually made an error over here. This should be... So this simplifies to, we know EY, so we divide both sides by EY. So this is finally the deflection at W3. So finally, these are the deflections for each of the point loads W1, W2, and W3. This is how you use Macaulay's method to find the deflection for a point load at positions X. Thank you for watching.